streaming.
And that's a nice kind of magic. It's actually science.
Right then, yes, it's streaming.
Done.
Hello and welcome everyone to the BreakerSpace stream. Now we are back with.
This is how Mark Gruber.
We're back with what? Huh?
Now this is how Mark Gruber starts.
Yes,
sometimes.
now how Mark Rober starts.
Daddy
Right.
started Mark Rover.
I need to get the chat window out, pop out. Can I? Okay, yes, I can. But I think it's better for me to keep the thing. All right. The last one is Twitch, right? That's Twitch.
It started. Okay.
Pop out chat. Yes. Nice. This game looks pretty good actually.
Yes, it does. Okay.
Oh no. The desktop audio will keep on going in. I think it was muted, thankfully. Else it will keep on looping in and out. Cool. Do I need to screen share as well while at it?
Why?
My design.
Okay, okay.
It's this one, right? Okay. So I'll have to screen share only this. Page. Let's add browser. No, not browser. I want to add what? A window. Window capture. That is a browser, however, an existing. Okay. I think I need to make it force HDR. নাহলে পরে ওটা overblown HDR এ দেখাবে। That is fine. Now how do I switch it on and off? I think I need to go like this. And then disable. Enable it, disable it.
Yes.
Yikes. That's why people use the stream decks so that they can just press a button and choose this, the scene gets swapped, switched. That works better. All right. I have too many windows open.
Will this park thing work?
Hmm?
Will this park that control?
Park, how do you input with that?
Then do match camera and you can draw
I mean, it's
match and then you click the camera.
not that you can't. You can command it to change. Like you can provide voice commands and it can show. Right, let's go into it. So we recently published you can show it like this. How about this? That is something more maybe we need to fix, and to add this camera over here maybe, right? That would get the angle better.
Yeah, I need to pull this thing little bit.
Or maybe make in fact, I don't even need this. I can just put it over there
Sure.
on this monitor. Oh, yep, that will be better. Right, cool. All right. So we recently published our video on Russian, so RSHN in the BreakerSpace. So Russian is basically Sanskrit for light.
Are you moving the table?
That's fine, nothing will happen. ওরকম করে ইয়ে ব্রেক করিস না.
Okay.
I really get my entire flow cut off.
Okay.
By the way, anything you're saying that is already capturing in the mic.
Okay.
So
got it.
you speaking slow, like as in a low volume, does not help the stream at all.
No. I speak at this level.
Huh?
This is my speaking.
Okay, fine. That part is fine. But the thing is, if you think it's not dangerous, then it's like
No, I'm talking about the camera.
that will be there. Don't worry about it. Cool. So Roshan is basically my umbrella term for all the light related projects that I'm gonna work on. So the main idea, main goal here is that I'm trying to build studio lights for myself. So right now the lights that I'm using, they are not really made for specific like a key light or fill light or hair light kind of a way, even though like mostly there are panel lights or strip lights that are doing their job. It works, but they're not really in any way properly set up for one dedicated purpose as you would in a studio setting. So that's what I'm trying to bridge the gap. Like, I want to make dedicated studio lights, preferably with no compromise whatsoever. So Roshan is a step towards that. One of the thing that I want to do is set it and forget it. So I want to make the setup in a way, keep them mounted wherever I want, and I be able to control them. My preferred mechanism is some kind of a web server, but I understand people might want to use web apps or some other different forms of control, and that's all is good. All like everything is it should allow all different kinds of modalities for people to access that thing, including there's bars and sliders and dials and stuff. And I want to demo all those things. They will come. Like the control, I will do the second part. The first part that seemed to me the most complicated to begin with was the driver, because that actually actively controls the power and dims the LED. And there are a lot of design considerations that you have to go through in order to make that happen. Even after this, I think everything pretty much worked out of the box, and it worked well. We were pretty floored, but I still think there's a one glitch that I need to solve in the next version, next iteration, and I'll talk all about that. So let me come to the details and into that. These are the boards that we have made in the first pass. One of them has the connectors soldered on. This is the one I used in the video to demonstrate that. And the other board is this one also, like the same thing, it works, but I kept this mostly for the beauty shots and like basically for photography purposes. We did not use this for the demo, but again, these are all same. I can just put this out of this board. This is the module, the Xiao ESP32C6 module that we have programmed with my firmware for this, and I can just put it on here. And now this board will work just the same as this board, no difference whatsoever. So in case for something happens, this one gets blown out, a capacitor pops or whatever, I do not need to go back and start working on it, fixing it. I can immediately replace it with this one and continue to move forward with it. So that's the idea. Also in ideal state, so as you can see, the footprint that is there in the board, I could actually really take the module and make it sit over here. As you can see, it sits completely like that. That's the footprint. But if I do that, I'll have to solder the module onto the board itself. And again, this is a prototype, and I don't want to commit too hard onto something. Like mistakes, like I trust myself very little on mistake making fronts. So I expect myself to make mistakes, which is why if I end up end up making mistakes, it will be really easy for me to solve it by if I could just pop the module out and put it somewhere else. So that's why I'm using these headers, and that's why I'm just putting the module, dropping the module in. If I ever make a like a more serious or solid version, so I might actually end up designing the ESP32 module by myself. It will save space and all, but for the prototype part where I needed to like choose parts for the MOSFET that we will PWM like for driving the channels, etc., I needed to see exactly how much current they can drive, how much power they can drive, and I'll detail those things. But those were the things I was focusing on, not the size and the packaging of the overall packaging of the board for that matter. So now we have reached a point where I'm pretty confident that this is gonna land, as in I'm gonna move forward with the second iteration, and then maybe a third one, or however that goes, we'll see. So in the first iteration, my goal was very straightforward. I needed multiple channels, or at least 5 channels. The reason I chose 5 channels is because I needed the red, green, blue, and cold and warm white. So if you see the connectors here, these are red, green, blue, and this is for warm and cold white channels. So I can drive. I don't have to know exactly which kind of LED module I'm driving. I can drive pretty much anything, and as long as they are DC LEDs, you can drive it from here, right? Yes, there is no constant current regulation here, and that's a choice that I made myself. So these are not constant current drivers, but they manage. You can manage the, even if you're driving an LED without a series resistor. So basically, that requires a constant current driver. You can use this, but you have to regulate the as in how far you can go, how far do you want to go with the intensity. You have to limit it to a certain point. Maybe you want to keep it at 50% intensity, so that it does not accidentally blow up. So but it does not happen like because we have the control dial and everything. So if you go watch the video, you'll see the web app side of it. I'm not going to demo the web apps today, but the GitHub repo is there. You can clone it and just npm run, npm start, and it will work. Give me a sec. Right, so the web application is not the focus today. What I'm going to focus on today is the schematic and the PCB layout that I have worked on. So basically, let's start from the overalls, right? So this is pretty simple design. There's not a lot going on. Here we can only see that this is the ESP. By the way, I'm using easy EDA because, as the name suggests, it's fairly easy to EDA. And also because JLC PCB was sponsor of the this project, as in the video. So I actually wanted to give the entire integration a try. So you can one-click order. That was actually helpful. I actually utilized that. So yeah, thanks JLC PCB. Anyway, this video is not sponsored, but I just wanted to be transparent. So that's why I'm using EasyEDA, and I actually had a really nice time here. Part of the reason, apart from the schematic and everything, this library is awesome. You can go to LCSC and JLC PCB assembled parts. You can look for them, and you can find out whether you want the basic parts and all. You can find those. You can actually see the specs in detail, footprint and everything comes all in. So that's one advantage that I have over my usual suspects like KiCad or what's the other thing? Flux AI.
Flux.
Yeah, I really counted on Flux AI,
Flux.
right? But
They got better.
they got better. Yeah, they got better. But that's the thing. Once you kind of lose your reputation, people find it hard to come back to you and stuff. So I will give Flux AI another try. But the reason I had challenges with them, like you couldn't draw planes, as in the if you want to create ground pores that is custom, like you want to create the as in the polygons yourself, like how the shapes want to be, etc. You couldn't do it very easily. It was like doing bare basic. If you just route some traces, like you are making like just adding a LED and a battery on a circuit board, those kind of projects would be good enough, like teaching kids. But the moment you want to do something custom, including like putting a logo on, it gets unnecessarily complicated, way more complicated than it has to be. So those kind of, so EasyED is like a good compromise on that.
So for this logo, how did you put it here?
You don't even have to think. That's the thing. You don't even have to worry about it in here. You can directly go to this thing, and then you can import images here, and
Okay.
yeah, they handle all those things. They actually know that there's nothing good that comes out of making people jump through multiple hoops. So it's just, okay, I will do all the conversion and how much bit depth, etc., what kind of format it needs to be. I'll do all those things. Just upload the image. Okay. So I uploaded the image that was not even a grayscale, right? But they converted into, so basically in order to show it here, you have to convert it into black and white.
But ours were not there.
Mine was not, so, but I uploaded it. They converted into, like as if traced it into the
grayscale.
So if there were gradients, because mine was, this BreakerSpace logo is high contrast, it was fairly easy. They could figure out what the edges are, and it was like, okay, yeah, so I got it. This is the logo, right? And yeah. If it was like a gradient and like lots of small lines and all, it'll be a little bit like you have to fiddle with it, like, okay, how much contrast do I have to show and all. But otherwise, they give you the control. But if the logo is high contrast, you don't have to worry about anything. Just very easy. Anyway, so that's not the, like, I'm not here to harp on the EasyED. I just wanted to mention that's the thing what I used for the project. Let's go into the module. Again, the module was Xiao ESP32C6. It's one of the Seed Studio. So if I'm not mistaken, Seed Studio is a German company. But Xiao means fast, and I think they wanted to use the Chinese name for, like, well, it has to be fast or fast or small. I don't know what. But yeah, it is very small. Let me show you. It's really small, and this is my favorite ESP32 maker board to work with at the moment. So this is the C6 variant. Apart from everything else, all the features that it has, it also has battery ports. So basically you can just add battery directly, and that you are done. You don't have to worry about the charging control, the, like, as in regulation and everything. All those things like charge control, regulation, everything is built into the board. And also there is like a antenna port, like you can add external antenna for better coverage, but it also has the cheap antenna, the small thing.
Okay.
So basically, if you're not like covering too much distance or like worried about signal integrity, this should be good enough for you. So yeah, so I'm gonna keep it aside. By the way, there's also this Seed Studio, Xiao ESP32F3 Sense. So I am also working with this. That they're very different project. Maybe we'll talk about this in future. Right now it has, should I tease? Tease? Okay. So right now it has a audio capture. So by the way, this Sense module has camera, microphone, SD card slot, like IPX camera, so not IPX, micro FL, but anyways, so this is a very high, like highly featured board, and right now it records audio, so it can record
audio
at 16 kilohertz
and video, because
video, if no, right now the firmware that is there, it records the audio at 16 kilohertz sampling rate. So basically voice and everything comes very well. You don't even have to run it through any kind of filter or like a low pass filter or like compressor, whatever, equalizer and stuff, because it already captures voice very well, and then it saves on the micro SD card.
Yeah.
So this is that, but expect more from it. This is a work in progress for later. Anyway, let's come back to Roshan. Right, where were we? Right, so let's go back to the schematic. Right. So this is the thing. The reason I went into this whole explanation about EZD and everything is so that I did not have to draw. I did not have to. Wait a second. Let me mute it, guys. Sorry, I'm back. Hello. Okay. Um, is the audio all right? I'm saying that the volume is shooting up a little bit. So if the audio or anything else was not right, you guys let me know, okay? I will go ahead and reduce the advanced. I'll reduce it 6 dB. How about now? I think this should be much more acceptable level. Right. Again, to stress myself back, I went into that whole thing because this footprint and the symbol and everything, I could just download from EasyEDS library. Just write Xiao ESP32C6 and you will, sorry, I got it C3. This one C3, not C6. But anyways, mine one is C6. The C3 is there. You can get the C6 as well from a different port, I think. I don't know where I got it from. LCC. Where's C6? They don't have it yet anymore. No. User contributed. Yeah, I think I got it from user contributed. But anyways, it is endless, bottomless. You will find what you're looking for. You don't have to make it by yourself. That comes included with footprint and everything. So this is the ESP32C6 board, and it had everything that I needed, including the enough of those drive channels. These are the get driver, MOSFET get drivers. I needed 5 of them, and aside from that, I just have power and ground. I am not using any other ports here, but I could if I wanted to. Aside from this, we have the power regulation, which this is the input, by the way. So if I go to our board, we can see this is the power input that is taking the 12 volt and going through a low pass filter and like a bulk capacitor. So this one is cutting off the high frequency noise, and this one is actually charging up the a power rail, and this is the connector, right? And the power output section is basically the driven output for the 5 channels. Each one of the 5 channels, the red, green, blue, I should probably turn it around maybe like this. It's very hard to show, like this is probably better in that way, right? So red, green, blue, cold and warm white. So those are all the different channels that are being driven from these rails, and I'll explain how they're related. So if you're seeing this R, G, B, C, W, those are basically coming from this gate driver section. So each one of the gate driving signals, so these are the signals, by the way. These sections, these are all gate driver signals that are coming and telling the MOSFETs, these are all n-channel MOSFETs, low size MOSFETs, telling them when to open, when to close, and depending on when these MOSFETs are open or close, this red, green, blue, cold and warm white channels would power up or power down, right? So where did it go? Right. So if you see, these are the gate driving resistors, This is 100 ohm, if I'm not mistaken. Yeah, this is the 100 ohm resistors. These are for charging up the gate. And we also added the pull down resistor. It was not necessary to add pull down resistor, but we did it anyway because that's just better, good practice. And I didn't want to be careless in my this design. This is the first prototype, right? So we did that. So this is very simple. There's nothing complicated going on, and I wanted to keep it that way. I could go like complete power trip into like trying to do pack as many features as I could into this, but I intentionally restricted myself from doing too much in one go because that's something that I have learned that usually causes challenges in the design. If you try to do too many things in one go, there's nothing wrong with making a feature packed device, but take short steps in your prototypes. If you try to make too many things in one go and something fails, the debugging is that much harder, right? So that's my, or at least that's how I operate. I'm pretty sure there are people who would be fine taking bigger leaps and getting away fine with that, but this is what it is. Now the design flaw I was talking about, I was alluding to earlier, is everything is fine. I just didn't need this big of a capacitor to drive each one of the loads, each one of the LED channels. My justification was for 1 microfarad or like, 1 millifarad or 1000 microfarad was because I wanted to make sure there's no flickering. I do not get too much flickering on any of the channels. I was planning to drive it at a pretty slow speed, which is like roughly I was 1 kilohertz range. So 1 kilohertz at 1 kilohertz range, I would suggest against doing that. Do not drive LEDs at 1 kilohertz. That's also another thing, but that is very easily solved in software. I don't have to worry about it. I can easily change it up to like something above 20 kilohertz, and that will be fine. Like that is doable. However, these capacitors, these big, huge capacitors here, make it really problematic for the dimming to work properly, because you see, they charge up faster because the MOSFETs open up faster and they provide enough current to charge up this capacitor. So even if you're running at a very low PWM, saturation to make these capacitors charge up happens really fast. So basically, by the time you're 25%, if you're 25% into dimming, probably the LEDs are all reaching to the point of like 12 volt and they're opening up fully. So that's something that I was mistaken. Shouldn't have done that. I'd be fine with like 1 to 10 microfarad capacitors. Probably that would be the next step. That's what I'll do, and I'll also drive it at the much faster speed. And aside from that, these are the hey, Momitas's audio is all right, thank you. Noted. And this is the AMS 1117, which is a 3.3 volt regulated input for power input for the module, because we have 12 volt input and we don't want to drive power, we cannot power 12 this module from 12 volt input, so we needed the 3.3 volt to run this. And instead of going through a complicated buck conversion or anything, I just went with something that is simple and trustworthy. So a normal linear regulator, even though it's not efficient, but none of this thing is. LED strip that I'm using is probably 50% efficient because of the resistor drops and stuff. So for the whole thing, the point is not efficiency and all. So we are not worried about those parts here. We are just trying to make sure the foundational parts work. They're not yet economically viable. They don't have to be economically viable or the most efficient or competitive devices on the market. They just need to make all the points, right? So that was the baseline here. These are the design, the parts of the design that I worked with. Nothing too complicated. Again, that is by design. It was it was hard for me to not add this and that, like a status LED from like battery pack, and it's all those different things, like making it offline compatible, etc. The point is, if I'm driving LEDs, then I need high power 12-volt input anyway, making this system, keeping the system up, like over time, with a battery or something, in order to just keep the values intact, like whatever the values you have set for each one of the channels intact. Those kind of features did not make much sense. So I was like, okay, fine, we'll go with something that is utterly simple, and that was it. So if any of you are joining now, we just discussed the schematic, so maybe you can, well, take a quick skim through on what we talked about. I went through the whole design. Now I'm going to move on to the PCB part, the layout tracing part. So this is not a very small board, right? I'll show you the actual thing all again. So this is like a, yeah, roughly 50 by 80, if I'm not mistaken, if I remember correctly. Uh-huh. Yeah, this is 50 by 80. 48 by 78. So that is not very small. I could have made it smaller, and if you discount that, if I went with same like surface mount resistors, surface mount capacitors, again, in this design, I did not go with surface mount capacitors because I was shooting for the bigger capacitors, as I talked about it, which is a poor choice. That's the only thing that I made mistake on. I should, like, I can easily go with a very much smaller capacitor just to eliminate the flicker. I do not need to make them bulk capacitors, these big charge holding capacitors. That actually does a disservice with the PWM. Anyways, but I would also go with SMD resistors, because for this time I was really not sure that how many times I might have to desolder them, rework the boards, etc. But I didn't really have to. Everything was pretty much on point, and hand soldering them were really difficult, as in not difficult, inconvenient. In future I might actually go with still, like JLC PCBs, assembly service or something, which would make it much more easier. Basically it will come assembled. I just have to program the module, and it's good to go. So that would be the thing that I will be going with probably in future. But in this time I was like, no, let's keep it ultra simple so that I can get to like open everything up and change the parts, and the parts need to be something that I can locally source, etc., etc. Like nothing fancy needs to be on the board. So that's what it is. The only thing that is fancy is this footprints that you can see of the MOSFETs. There are 5 of those MOSFETs driving each one of the 5 channels, the RGB and cold and warm white channels. So that's probably the only, that's AOSMDs, 3400 N-channel MOSFETs. So those are the only ones. Other than that, normal through-hole resistors, normal very like basic LDO, and normal barrel capacitors, and yeah, that's pretty much it, like terminals and all. Right. So I went with 2-layer board. If you see here, if I make the top layer go away and put the bottom, so the tracing is a little bit hard, because I have to go here, then trace through this and come back out with that. Would have been much easier to lay them out, put them closer together if I was working with a 4-layer board, because there would have been a much better crossover points. I could trace the lines back and forth. With 2-layer board, the problem is if something is coming like this line, there is no other port here on this side that I can use for the 5th input, right? So the 5th input has to come from the other side, which means this entire line is blocked. So if I have to take anything from this side to that side, I have to go dig down and take it from the other side. And if I do that, then from the other side I cannot take anything from this side to that side. So it's like a mess of things. If it's, oh sorry, I need to switch the my bad. Sorry if anybody's watching. I was talking about the board here. This thing. My bad. I was talking about this board here. Uh, uh, so these are the MOSFETs, and these are the very normal gate resistors. This is the pull down resistors. These are the capacitors, and this is the terminal. This is the output. This is the our this is our uh, linear regulator. Yeah, that's pretty much it. All right, cool. The point I was trying to make is that because of just two layers, tracing is hard because you cannot cross over, you cannot jump over something. If you have 4-layer boards, it is that much more easier because you get basically 4 times as much. It only 2 times as many layers, but you get 4 times as much, like as in flexibility in tracing and routing your traces. But I was intentionally trying to keep it simple. So that is done. Next board would be 4-layer. And yeah, it will probably be much smaller as well. So I was not sure that if there would be multiple of delta versions. So delta is the first iteration where I just work on making things work. So that's the delta 1 here it means, and it was done in February of 2025. So that's the marking here. There would not be a delta 2. The next one would be a sigma 1. So sigma is, so I have a design principle where it goes like effective, efficient, elegant, and extensible. So effective, when I'm working on the effectiveness, it's delta. When I'm also integrating efficiency, so next board would be efficient as well. That's where it will be the sigma board, and it will be more on the line of like, okay, now we have understood that the things work. Now, how do we make it work better? So that would be the goal there. And of course, I'll again talk all about it. But yeah, so this is the basics of this project. I was wondering if there is any questions or comments or from anybody. Let me check the chats. Nope. I think there were a couple of viewers, but okay, nobody commented or anything. That's fine. Still, welcome everyone. If you have watched, like, stayed around and watched, thank you for that. Even if you're not watching right now, that's fine with me. Drop by anytime you like. The videos will be up, even though they'll be unlisted. They will still be up in the deep dive playlist. So be sure to check that one out for other deep dive live streams as well. Somebody is spamming on Twitch. I have no idea what they're talking about. But dude, make better use of your time. Spam somewhere where people are watching. All right. Let's get back to our other stuff that we have. Like, I have a couple of more things that I need to work on. So give me a little bit of time. So this was mostly about covering the RSHN's part 1, which is the drive, like the drive module. So which is this. So next version would be sigma 1. Along with, I'll also work on the control module. So keep your eyes peeled for that. We'll talk about it more in future. So let's go back to our usual programming. So let's disable it and let's get out of it. Nice. Cool. All right. So now that we have talked about our RSHN, let's put it back in and we will come back to it maybe in another stream or next stream. If you guys have any question or comment or something, you can even comment on the video itself, if you have any question, and I'll try to answer that or there, or I'll pull them out the next in the next stream. So come back for that. I am right now going to work on a couple of Raspberry Pis that I need to set them up with battery packs and all. So basically they are going to be my always on devices. So this is one, and the other one is here. So I call it Chiranjeevi Pi, maybe here. Right, standoffs and the big split. Cool. I'll tell you, I'll talk about more the details of what am I opening up. This is not an unboxing or a product review or anything. These are the things that I need to do anyway. I'm just more excited to do that when there are audiences. So if any of you are watching, thanks for watching and joining the stream. Let's go back and start setting them up one at a time. I'll keep this one Chiranjeevi Pi aside. Let's work on the OTG first. So if I'm not mistaken, this board is an OLED hat for Raspberry Pi Zero. The challenge that I have in here is this one does not have any header, which is a problem. I need to add in header. Should I add in header, or should I add the inputs from these inputs? So this is basically SPI. This uses SPI protocol, so you can see the data in clock. Oh no, this is not SPI. This is I2C. Right, so this is an I2C OLED hat, or maybe it supports both. I'll need to check. Right, so this supports both SPI and I2C, right? I think the camera needs to be. Let me reset my camera so that it's visible even when I move. Edit, transform. I will need to crop more on this side. Sorry. Oh, 80. So I did 280 on that side, so I'll do 360. Okay, so that should make it a little bit more better for you guys to see my face on the screen. I'll need to change the camera positioning. Bear with me for this stream. Anyways, so this one is an OLED hat that will give me a pretty good view of whatever is happening with this board. So this one is what I call a Pi OTG. So it's on the go device. It has all the different, like it has a USB hub integrated along with a network port, like a LAN port. So it's really extensible. I can add any kinds of devices that I want with it, and it connects with each other through pogo pins. So if you just give power through this board, it powers everything up. including the peripherals that you connect. Now the idea is I need to attach this over here and put them all together in a sandwich. Only challenge that I can see here is there is no way for me to do that without adding the header pins first. So that is something that I need to work on next up. Right. Okay. Note to myself, need header pins for the Raspberry Pi. We'll have to come back to this in the next stream maybe. Let's keep it aside. Okay, how about the other board? How about the always on Pi? I call it Chiranjeevi. So this should be fairly straightforward, isn't it? So this is the Raspberry Pi 5 4GB model, and there's no hat. I haven't added any hat here, but I will probably have to, especially the NVMe one. And once I do that, uh, this is going to be one of the servers that I want to set up for most of like many of my critical home lab use cases, and hence I do not want it to go down even in the case of like a longer outages and stuff. I want it to stay up, and that's why I wanted a power module that kind of does power ORing with power path and everything, which keeps the board up even in case of extreme power outages, or when I can maybe take the board from one place to another and set it up there with a alternative power supply. But during that transfer I don't want the services to go down or anything, so this integrated battery pack and all would help with that. So that's the idea here. um, I can see that I can just go ahead and set it up. I'm not sure if I want to use the base because it does nothing good for me. It just makes it harder for me to access the battery packs. But if I don't add this, then there's a potential for the batteries to basically fall off, like maybe slip from my hand and fall off to the ground, which would be bad. We should avoid that. So, question, or rather, decision time. I think I'll put the back cover on and see if that helps. If it doesn't, if I have to open it up and it feels frustrating, then the next time on I will not put it back anymore, right? Okay, so now that we see here, the idea seems to be like I have to put these standoffs, then these ones from here. I hope there's no directionality to it because I'm just putting one after another without noticing like if something has to be up or down, but does not really seem like it makes a difference. So let's just go ahead with it. Hopefully we might not need to backtrace ourselves. I guess it required a little bit of more explanation on what it is and what's the features of it. So let's quickly cover that once I add the fourth and the final standoff. Right, now that I have here, so this is, as you can see, it's a battery holder on this side, and on this side we can see, oh, it's written, this is a UPS hat, right, from Waveshare, right? So what it does, it makes the Raspberry Pi to stay always on, and you get the monitoring and everything else, like as in integrated. So as you can see, this um, these standoffs, these are actually pogo pins, the small ones, these are pogo pins. So these pins connect with these pins backside, so this side. So here's a 5 volt and ground, as well as the I2C line over here, so which is what these ones connect with when we put it here, and through which, so the battery monitoring system, so battery management IC can actually send back uh, details to Raspberry Pi saying what this battery status is, so you can monitor it much more easily, which is very handy. Along with that, there's a USB port that is 5 volt out if you need 5 volt out for some matter, and it's also 5 volt in, which is the USB-C port, right? And this is the switch which lets you turn it on and off. So like as in on Pi 5 it's not that much useful because Pi 5 integrates the power button here, but on Pi 4, which it's still compatible with, so on Pi 4 you would appreciate having a power button, because otherwise pulling the power out and power, like put it back in, that's the only option to reboot the Pi. And there's also a boot button here. I don't know what does this boot button do, because from what I can see there is absolutely nothing that pulls down the boot pin. So basically, unless there's something happening over the I2C line, it does not do anything to make the booting have any effect on the booting. Or maybe pressing this boot button does something, tells something to the UPS IC over here to conduct accordingly, maybe to channel more power or be at a higher power mode or something like that. I don't know, maybe we'll need to look into it. Let me try and open up Waveshare's UPS hat page so that we can learn about it. I really would like to know. All right, let's share screen. Window capture, existing Firefox lookup. Okay, right. All right, so Waveshare, what is it? Raspberry Pi UPS hat. Let's see. This one is right. I bought it from Robu, by the way. This wiki would be the one we should go into, but let's just take a look here. They're surprisingly open about their stuff. This is not it. This seems like a different design. Maybe our one is different. Let's see. This is the one, but this is 4 battery version. Our one is 2 battery version. It has to be this one. Yeah, UPS had D, right? So this is the correct one. This is the correct one. If we go now to the images, we get to see, yeah, this is the correct one. They're surprisingly open about their designs, so they will tell you exactly all the things that are happening in here. By the way, let me show me webcam. Go down this and okay, yeah, anyway, sorry, managing the OBS screen. I kind of lost my chain of thought. So I'm here to take a look at what is happening with this board. Let's have a quick look. Features at a glance. By the way, let me know in the chat if the text is too small or something. I need to change anything. Otherwise, I am unsure. Right? Let's take a look at this. We might have to go to the wiki page. Okay, the MCU chip, this is the ground pin. As I said, like these ones, the I2C pin and the ground like power pins, those are the 4 pins. There's no other boot select pin that is actually being accessed, so I don't know what is going on with the boot. We will text search on the wiki page for that, and this is how the um, battery status looks like in if you have the I2C battery access status access. And because it connects to the board from the back side, you still have the top portion open for adding any other different kind of hats like the NVMe hat or this kind of things. So that's good. Right. Power output, everything is good. I need to understand what the boot button is doing, so let's go over here. Let's search boot. If any of you watching this and are on the page, I'll go ahead and copy paste it in the chat. So if anybody is in the chat, you can go to the wiki page and try to look for yourself, in case I miss it. I can't see anything related to the boot. Yeah, like what that boot button is for. And if for anybody uninitiated, I'm talking about this. I'm talking about this boot button here. What does it do? We already have the power button here. Maybe nothing to worry about, but I just... Oh wait, they have the schematic, right? Yeah, this is what I'm talking about. These people are surprisingly open about their design, and I love it. I can't appreciate it enough. I think more people should do that. They should have this kind of clarity with their stuff, that much of confidence with the stuff. Like they are making these things professionally, and they have every reason. Most of the, like, I'm not naming names, but most organizations will be like, oh no, we want to like hide it, we want to make it proprietary and stuff. These people don't care. They're just giving it away. Go ahead and make it, make it your own. I love their philosophy. This is good. So there's a fuse as well. Nice. So this is the monitor, as in reporting chip, the I2C one. Cool. These are all the MOSFETs that are doing the power, this power stage. How many are there? There's 6. Yeah, there's 6. Right. USB host over here. Do I miss anything? Does not seem like it. Here we have high enable. Is this the boot? No, this is the switch. This is the enable switch. This is the toggle switch that enables. The one you flip. Where is that boot? And why does it bother me so much? Like, why can't I just move on like a normal people? What? There's nothing. Guys, what's happening? What's going on? Let's see if there's any traces or something that we can see from here. So the boot is coming from the warning. Uh-oh, I need to switch the scene. So if we can see, the boot is coming from, the boot trace is coming from, is going towards probably this LEDs, and the other end is coming from, not entirely sure, it looks like some kind of, this is the I2C driver probably. Oh, okay. Does it send boot information over I2C? Like, can it call for boot over I2C? That would be pretty interesting if it calls to boot the board over I2C. Let's go back to the schematic and see if that is possible, or something that they're doing perhaps. So okay, so that was this IC, right? Where did it go? This one. So it was this. The LEDs, where do they connect? V1, V2, and so this one go from ground to V1 and this over V1 to V2. So let's see where the V1 and V2s are, power rails are. This, okay, so this means the middle of the power source. So this is where is being driven at the middle. So this is where the power ordering is happening. So that makes sense. It's a halfway through the battery. So okay, so this is the battery mid essentially. So if okay, so if either of the batteries suffer any kind of problem, this would be able to detect comfortably. So this is for battery 1 and this is for battery 2. This is the midpoint between the batteries. This is the, like, those batteries are in series. It looked like they're in parallel, like, because they are, the way they are kept in here, it looked like they are in parallel, but apparently not. They're not in parallel. Am I tripping? Yeah, they're not in parallel. This is a 2S battery. Huh, that makes sense. So that basically falls back to the same design that I'm working on with Amar's core, which is 25 watts UPS. So this is the same thing. So that's also 2S, because it's that much easier to basically take any kind of voltage like 12 volt or something, and then basically take it down to 8.4 volt, and then from there the lowest voltage from 2S you can reach is 6 volt, because 3 volt each battery. And so as long as the output voltage is 5 volt, you can just work with a buck converter. There's no buck boost required. So this is good. Okay, that makes sense. Shunt resistors, and shunt resistors coming from these two MOSFETs. I don't know which one is which. Those two. What is the third one? Where is the third one? Wait. This is probably a different one. This is probably, this one is probably the USB host chip. Anyways, I would need to look up if there's any kind of boot request going on over I2C. So that's something for me to take a look at. Other than that, this was pretty clear cut. This is very like pretty well designed. I liked it the way they have implemented it. It made sense. Again, it's not complicated. They didn't do more than they had to, but that's good design. That's exactly how good design should be. It's not much, it's not less, it's just right. All right, so now I have to put the board and I need a screwdriver. Give me a moment, I'll bring my screwdriver. This one's fine. By the way, while at it, this is another board that I'm testing, like basically charging, discharging. Right, it has charge. You can see the LEDs. This LED is lit up. So this is also a 2S setup, which actually does boost and provides 12 volt. It takes USB power, or you can provide normal power in as well, 5 volt power in as well, and it will give you regulated 12 volt output, which operates in the boost topology. And I'm trying this one out for the UPSs that I'm working with. Sorry, the router UPS that I'm working on. So I'm evaluating this as a comparison, feature comparison. Something like what is baseline. You have to take something as a baseline so that we can make better designs on top of it. All right. So this is really tricky to do that by hand. I think my best bet is to align the screws from top and hope that the bottom actually connected the right place. I will verify that anyway, so I'm not connecting power or anything before verifying that, so there's no issue. There should not be any issue with that. Okay. Let's hear some music. I mean, like, nobody's watching anyway. Oh no, people watching. Wow. Okay. Cool. I was going to watch some music, right? This is a music from Coke Studio.
Coke Studio, Season 15. Coke Studio, Season 15.
This one is called Jhol. One of my earworms recently. Should I use the volume? If any of you joined the stream recently, hi, thanks and welcome. Make yourself comfortable. We went through a couple of stuff, but now we are kind of getting things back together. I used the wrong screws by the way. There are two different kinds of screws. Oh wait, why am I playing music? You'll get copyright strike again. Damn it. I keep on forgetting that I'm streaming on YouTube as well. On Twitch it won't be a problem. It'll just mute that part and it'll go on fine. On YouTube, yeah, that's the problem. All right, so now for this part of the business, I first need to make sure the contacts are right, which it seems to be. Fine. Now I need 21700 cells, which just give me a moment. I'll bring it back right up. No battery question. I think the battery is right for the Chiranjeevi. Can I hear it? Right. Akshay. Alexei. Hey, Alexei. I do not understand. Let me translate it. What you're asking. I do not understand what do you mean by that, but thanks for watching. All right, so these are two of my 21700 cells. These are bigger than 18650 cells. If I'm not mistaken, this should be 5 amp hour, which is basically the 5000 milliamp hour. Yeah, it's written 5 amp hour, right? So these are almost like double the size. Even if it doesn't look like they're double the size of the 18650 cells, their capacity is actually double, and they're really heavy, like pretty heavy. Right. So from backup perspective, they should give good backup. These are new cells. As you can see, there have not been like any kind of, there hasn't been any kind of what do you call that thing, a spot welding marker or anything. So these are really good new cells. Let me bring my multimeter and check that if they're in a serviceable, like as in have they depleted too much or something, because I haven't used them quite a bit. And please excuse the dirt on top of my multimeter. It stays open and my place is very dusty. So anyways, let's see what's the voltage that they're carrying. So 3.6 and 3.6. So they are actually pretty healthy. They are doing fine. In fact, I probably kept them at 3.6 volt anyway, because that's where you want to keep the, like, store them for long term. Ideally they should be kept and stored at a 3.6 to 3.7 volt. All right, so let's go ahead and put them in there. I am taking a leap of faith and going by the markers. I'm not very sure that if the marker is correct, because from the schematic it's a 2S board and they should not be terminating on the same side, right? But the marker says plus this way, minus this way. Let's see. All right, so they went in. I do not yet know whether it works, but I can verify that by connecting my monitor to this and switching the input on that monitor. Give me a moment. Sorry. Let's connect it to this one. And I would probably be wanting to power it from this, right? Okay. Oh no. Oh no. Oh no. The HDMI connector is really messed up. Oh shit. I think it's gone, isn't it? What's wrong with the Raspberry Pi Z, like HDMI connector? Why does it happen with this anyway all the time? Okay, so let me give it USB-C PD. I'm gonna switch my display to is there any LED? Okay, so the LEDs have lit up, as you can see, blue LED. The status LED looks, so charging is happening. That's good. The first input, let's go to HDMI 2 and let me try and press boot. Oh, okay, sorry. I first have to on it, turn it on, then press boot. No? Yeah, it did work. It did work. Wait. Nope, there is no output. This should power on, give power to the Raspberry Pi, which you can see if the green LED is actuating. So that means it should start powering on, and it probably has powered on. I think the HDMI cable is broken, so that's why I'm not getting any output. So let me revert back to using a different HDMI cable. Yep, that is the reason. I'm pretty sure. Yikes. So that HDMI adapter is gone, apparently. I need a plier. All right, guys. The stream has gone well for far too long. Now it's time for us to kind of wrap it up for the time being. Where's my plier? God damn it. Oh, plier is in the other room where I kept it during. Okay, never mind. I will open it up later. All I need to do is check it with a different display cable that I can show over there. Okay, let me try and do that. I'll have to open it from here. Sorry, Raspberry Pi. Oh, I don't have to worry. It's still on because wait. It's still on because of course that's the whole point, right? So I can turn it on and move over here. Where's my USB cable? Nope. This is the one. Let me try and put it with this. This is bad. I hate this. Why, Raspberry Pi? Why? This broken micro HDMI, the worst HDMI connector. Like I don't know why like they made this spec. This is yikes, big yikes. So all we are trying to do is nothing fancy. Just see if the Pi has turned on, right? Oof. God, these HDMI cables are so much of a pain. And in case you're wondering what am I trying to do, I'm just trying to connect a micro HDMI connector to this Pi and switch the input. Yeah, so this is Raspberry Pi's. I hope you guys can see it. Let me try and maybe switch this in. Need the Logitech, right? Is it here? No, give me a second. Let me try and get, never mind. Let me make this, reset the transformation so that you guys can see it. Oh, the text is too bright. But anyway, you can see the white light, that is basically the wallpaper of Raspberry Pi that is there. It has all the keyboards and mouse and all these things in a retro doodly way. Anyways, so that worked. It doesn't even have power here, and I can take it out. Yikes, please don't break HDMI cable. Thank you. Holy shit, it's panic inducing, man. I hate micro HDMI cable. I hate it. I absolutely hate it. One of the worst design choices ever. It's worse than the people harp on the 12-volt connector. This micro USB micro HDMI cable is worse than that. Anyways, so that kind of concludes our stream for today. I'm gonna put it on charge so that it charges for a while, because as you saw, it was at 3.6 volt. I'm gonna charge it up to full and then connect it back on. I'll probably remote in and set it up. Maybe in the next video we'll talk about what am I setting it up with. The idea is in this Pi. Where is it? Give me a second. Let me just turn it off. So the idea is on this Pi, I am going to set up all the mission critical kind of home lab services, monitoring tools, the backups and syncs, etc., so that even in case of extended power outages, if I want to move the server, physically move it elsewhere or take it away somewhere, I can do that, and it will still be safe, sound, and operating. Like it will still be up and running even on the move. So that's why this whole as in to go with this whole extraneous process, but I am pretty sure it will be all worth it when it's completely done. So let's come back on the next week's stream. Thanks anybody and everybody who is in the stream and watching, and we'll see you guys next time. We actually started only to talk about Russian, but then we moved on to setting up the pies as well, and I'm glad that happened. Okay, until next time,